Now let us see the integrated rate equation for the first order reaction. Now for first order reaction, let us take an example that A moles of A changes to B moles of B. Now we know as per the rate law, the rate is equal to K A to the power n, where n is your 1 because it's a first order reaction. Also, we know that the rate can be written as minus dA by dt, with there this dA is again the same, the small change in the concentration of A for the small time interval delta t or dt. This negative sign shows that the concentration of A is decreasing. Now this is how we can show that the concentration is depending upon the rate depends on the differential of the concentration, and now these two rates should be equal to each other. So what we can make out is that this minus dA by dt is equal to Ka to the power 1, which we write as Ka. Now this same equation therefore can be written as minus dA, because we will bring the A here and we exchange the A with the dt. So we will get minus dA over A is equal to K dt. So this is what equation we get. Now we have to integrate this equation taking the limits. Let us see here how it can be done. Now integrate equation taking limits. So minus dA by A is equal to Kt. The limits taken will be at this on the left hand side will be A naught to A, where we know A naught is the initial concentration and A is the amount of the reactant A left out at time t. So initial time is 0 and the time is taken as t. So this is how we will integrate with these limits. So what we do is we know the integration of the dA by A is natural log A. So this is minus natural log of A minus natural log of A naught is equal to Kt, because the other will become 0. Now what we can do is we can open this up. It can be written as Kt is equal to natural log of A naught minus A, which becomes natural log of A naught upon A, or which can be written as, if we changes this into log base 10, 2.303 log A naught upon A upon T. So this is the rate expression or integrated rate equation for first order reactions. All first order reactions will follow this equation, and with the help of this equation we can find out not only the rate constant at any time, we can also find out the specific rate reaction at any time during the first order reaction, or we can find out the amount of the substance left at any time t. So that's a very valuable information and the equation which we get for the first order reactions. Second thing, we can also now find out what can be the half-life equation.